In this video, we're introducing the breadboard, and we'll illustrate how to set up a circuit on the breadboard. And then we're going to work an example that I would call a concept circuit. It's a circuit with 3 light bulbs in it, and there's some really tricky arguments that have to be made for how the brightnesses of those light bulbs will change when we modify the circuit. So the breadboard is the thing you see on the left here, and this is a rapid prototyping device for electronics. So all the typical electronic components like resistors and capacitors and inductors, they all have wires that will clamp firmly into these little terminals, so you can quickly set up a circuit and then test the properties of it to make sure it's doing what you want before you start soldering things. On the breadboard, I've highlighted some strips in yellow, and what I'm doing here is illustrating holes that are actually electrically connected to each other with a continuous piece of metal on the back side of the breadboard. So over here by the blue line, all of those holes on that vertical strip are electrically connected to each other by a continuous metal strip. Next to the red line, same deal, but those are isolated from the ones that are next to the blue line. And then I get to my horizontal strips. So each of these groups of 5 is a little horizontal strip that's electrically connected. They are not connected across the gap in the middle of the breadboard. So each of those strips is just 5 connected holes. I highlighted 4 of those groups of 5. Those groups are not connected to each other. They're only connected horizontally across those sets of 5 holes each. What you see on the right is a container of miscellaneous jumper wires. So this allows you to connect these metal strips to each other, and that way you can spread your circuit out and organize it the way you need it on the breadboard. So this is the concept circuit that we're going to tackle. We're actually going to wire this on the breadboard, and every one of the resistors here is actually a light bulb that I took out of a set of Christmas lights. I can see that all the current in the circuit passes through R1, and then I end up with this parallel branching where R2 and R3 are wired in parallel. I can tell for sure they're in parallel. I know the potential is the same at the high side of R2 and R3 because they're both connected directly with wire to this upper node. So I could call that V for now. And the potential at the low side of R2 and R3 is the same because they're connected to this bottom node directly by wire. And then I noticed that that node is connected to the negative terminal of the battery, so I could just call that 0. So definitely, I have the same potential difference across R2 and R3, so those are wired in parallel. So I have 2 questions about the circuit. First, how should the brightnesses of the bulbs compare in the original circuit? So one of the key points here is if the amount of current going through the bulb is greater, certainly the brightness will be greater. But I can also say if the voltage across a bulb is greater, well, that would make the current greater, so the bulb would be brighter. And we're going to use both types of reasoning as we answer these sorts of questions. So there's a couple ways of answering the first question. The simplest way would be to say, well, all the current in the circuit passes through R1. I'll call that I. And then when I hit this node and I pass through R2 and R3, that current gets split into I2 and I3. So only part of the total current is going through each of those light bulbs, R2 and R3, so they must be dimmer than R1. So we have that R1 is the brightest, R2 and R3 are dimmer since the current has been split. And in fact, you can say R2 and R3 are equally bright because they have the same voltage across them and therefore the same current through them. All right, question 2 asks, what happens to all the brightnesses if we remove R3 from the circuit? Well, clearly R3 turns off because we removed it from the circuit, but what happens to everything else? And the key here is to think of the simplified circuit you would get by combining the 2 resistors that are in parallel. And I'm just going to replace that with Req. So this is really our original circuit, just writing down the equivalent resistance of the 2 parallel resistors R2 and R3. And I know something about the comparison between the equivalent parallel resistance and the individual resistors in the combination. The equivalent resistance is less than the resistance of either one of the participant resistors, so less than the resistance of a single light bulb. So then I do a comparison. What happens if I just pluck R3 out of the circuit? Well, the total resistance of this circuit is bigger than the total resistance of the original circuit because R2 is bigger than Req. So R total is bigger. What does that mean about the total current in the circuit? Well, I'm thinking about Ohm's law here. So I total is V over R total. And because I have a bigger total resistance, I total goes down. Since all the current in the circuit travels through R1, I just figured out that R1 has a smaller current going through it. Thus, it's going to get dimmer. I can also conclude from Ohm's law, V equals IR, that if I have a smaller amount of current going through R1, that means there's a smaller voltage drop across it. So V1 got smaller. But my two voltages across these resistors must equal the battery voltage when I add them up. If V1 got smaller, then V2 got bigger. And if the voltage across R2 got bigger, that bulb is going to shine brighter. All right, so this is the classic mental gymnastics of a concept circuit. Okay, now let's take a look at how it actually turned out in the lab. Okay, here's the setup for our first concept circuit. I've got a power source over here that I'm going to set to 3 volts DC. Out of the high side of that power source, I'm connected to the red strip, and I'm going to use that as my plus terminal for any circuits that I put on the breadboard. And then connected to the blue strip, I have a jumper wire going to the ground of the power source. On the right, I have a selection of jumper wires that I'm going to use to just kind of spread things out in a convenient way. And then our resistors here are just Christmas lights, and what we're doing is looking for qualitative changes in the circuit based on removing one of these Christmas lights. I'm going to start by jumping to one of the horizontal strips with this orange jumper, so I'm plugging that in to the high side, the plus terminal, the red strip, and then I want to get all the current to flow through this light bulb. So I'm going to plug it between 2 of the horizontal strips. So the leads coming out of that light bulb, one is in strip number 6 and one is in strip number 7. It's a really common mistake when students are first learning the breadboard to plug both leads of a circuit element into the same horizontal strip. But that would just connect those 2 leads with the metal strip and no current will flow through the circuit element. So you've got to jump between 2 different strips to get current to flow. All right, then I'm going to jump down to a new horizontal strip just to give myself some space here. So I went from the negative lead on this first light bulb down to this new strip. It's like strip number 13. Now I've got to set up my 2 lights in parallel off of this new strip. So I'm going to put 1 lead of each of these lights in that strip number 13, and I'll just bridge them over to strip 15. And I'm going to spread them out a little just to make it easier to observe them. So we got at least a little separation between the bulbs. And then I need to get the low side of these back to ground. And so I'm going to have to jump down to a new strip just to give myself some space. And then I'll get myself back to ground. Again, that's the blue vertical strip. So I've turned on the power source at 3.5 volts. And on camera, it probably just looks like a bright white blob. Well, R1, that first Christmas light, is glowing very brightly. The other 2 bulbs, you can actually detect a dim glow on them. It's just barely glowing red in the filament. So I'll try to get some up-close photographs of this so it's easier to do the comparison. But real quick, what the experiment is to remove R3, one of the parallel lights, and then see what happens to the other 2. So I'm just going to pull it out real quick. And perhaps that's visible on camera. What happened is the very brightly glowing R1 just got dimmer, and then the second one, R2, that was in the parallel combination, just got brighter. So if it wasn't clear from the lab video, this is how it turned out. In the initial state, this bulb R1 was shining very brightly. And if I look at this picture, I can barely see anything happening with the other 2 resistors. Now, in real life, I was able to see the filament on these glowing just barely. It was just barely a visible glow. So definitely dimmer than R1. Hard to say if they were equally bright in their dimness, but qualitatively this is consistent with what we expected. And then I look at the final state, and here's R1. It's definitely gotten dimmer, as we predicted, and R2 has definitely gotten brighter. So that's it for our introduction to the breadboard and our first concept circuit. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.